So this will be the third and final lecture on blackbody radiation. So what we were doing is we were going through Rayleigh and Jean's derivation of radiation from a blackbody spectra, trying to get the equation of this curve right here. Again, we are looking at a cavity where the walls, the atoms on the walls are oscillating, giving off radiation. Some of that radiation makes it outside. Right here. And again, we're defining J, this radiation that gets out, is the power coming out divided by that little area right there, exiting between F and F plus DF, a little frequency range. And again, it had to fit certain criteria right here. The wavelength, if you plot it out versus wavelength, the peak wavelength times the temperature should be a constant. And the area under this curve should follow sigma t to the fourth, where sigma is some constant called Stefan-Boltzmann constant, 5.67 times 10 to the minus 8. So what we had said, Rayleigh and Jeans, they said, let's assume a cubical box, a metal box, and they converted it to an energy per volume, and they noticed there was a factor of C over 4 you need to put in there. And then the energy per volume, they converted into how many oscillators you have times the average energies. That would give me the energy per volume. And counting up the number of states you have in there for each frequency, since you get standing waves in that box, we get this number right here. It goes as the frequency squared, because at higher frequencies, shorter wavelengths, there's a lot more combinations of waves that you can fit in there. And then the last thing we showed was that the average energy we could write like this. It's a distribution. E to the minus E over KT is called the Boltzmann distribution, where K is a Boltzmann's constant. It's not the Stefan-Boltzmann constant. Boltzmann, 1.38 times 10 to the minus 23 joules per Kelvin. So this is a joule per Kelvin. When you multiply it by the Kelvin, it's just joules, joule. You can't have any units in the exponent. So this is what we want to integrate right here. So that's where we're going to start. And hopefully it gives me that curve. So let's just first look and try to do this integral right here. So we got the integral from 0 to infinity of e to the minus e over kt e dE all over the integral from 0 to infinity of this without the e to the minus e over kt dE. Okay, so let's just work on the top right here. It looks like the best way to integrate this is just by parts. Let U equal E, and let dV equal the rest. E to the minus E over KT dE, and then du is dE, and V is the integral of that. The integral of that is still e to the minus e over kt, and then times it, and then what do we have? We have minus a kt right here. It's flipped right there. So there is the uv. So if we just look at the numerator right here, the numerator is e times this, which is minus kt e to the minus e over kt, evaluated from 0 to infinity, minus the integral of v du. Well, the v would make that a plus kt. I can pull that out in front. And we just get e to the minus e all over kt dE. Okay, and then the denominator I'm not going to touch. I'll just leave it as the integral from 0 to infinity of e to the minus e over kt dE. Well, when we plug this in, when you plug an infinity in for e, this term is going to make it 0. E to the minus infinity is 0. And when you plug in this one down here, when you plug in 0 in for that E, you're going to get 0. So this term is gone right here. That term's gone. And it just so happens that that integral and that integral are exactly the same. This is also from 0 to infinity. So we can just cancel those two. So it looks like this integral isn't that bad. It's just, this is just kt. kt. Okay, so now we can take that kt, plug it back in over to here. And so what this whole thing becomes, this j, we might as well just write it right here. We get j of ft df is equal to c, we end up with 8 over 4, that's 2 pi. L cubes canceled out. We got an f squared. We get a k. This whole thing was just kt. And we got, I forgot, there was a c cubed down in here. There was a c cubed from the previous board. So that's a c squared. C squared. 2 pi, just wanted to make sure right there. It's 2 pi kt f squared df. Oh, my df. Okay. Now, if you were to plot this out, that's certainly, here I'm plotting it out versus wavelength, but if you were to turn that into wavelength, it would not look like this. Remember, this, if you plot it out during frequency, this is going like a, it's going like a parabola. It's going like f squared. If you were to plot it on this scale right here, it would look like this right here. It's not bending back down right there. And if you tried to integrate this thing, you'd get infinite right here. It would say every radiating object emits an infinite amount of energy right here because the area under the curve is the total radiated power. So they called this big problem right here, this thing going up like that, instead of bending back down, they called it the ultraviolet catastrophe. Ultraviolet catastrophe. Okay, big thing right here. So this was the big puzzle. Why don't you get this classically? All right, why does this thing bend down right here? And it was actually Max Planck that tried to figure out, how do I solve this? Where's the problem with this derivation right here? Most of this stuff seems fine right here. But Max Planck said, you know, it's really this that I think is the problem right there. How do you calculate the average energy right there, or the average? And it really comes down to this right here, this integral right here. This integral right here, what do I want that integral to do right there? What I'd like for that integral, I'd like it to be fine, because at low frequencies, at small frequencies, I want this to work out pretty good. So this should be good at low frequencies. But I want it to bend down at high frequencies. This is high frequency over here. Short wavelength is high. So I want it to go to 0 at high frequencies. So I want it to go to 0 at high frequencies. So how can he do that? Mathematically, how can I make this integral do that? Well, let's look at this integral for a minute right here. If we were to plot out that, first of all, that just the exponential term right here, the exponential term it kind of, looks like this. There's the there's your e to the minus e over kt. And then the other term, which is just e, just looks like that right there. So there's your e term. And when you take the product of the two, well, you get pretty much 0 over here. This times this is 0, and over here 0 times some big number, still 0. You get something that goes up and then comes back down right here. So that's what this curve kind of looks like right here, just what we're integrating right there. So I'm just going to kind of draw that curve right here. It kind of goes, okay, we'll just draw it up and then bring it down like this right here. Okay, so it's going to grow up, it's going to get bigger and then back smaller again. Now you notice when you first learned how to integrate 1A, math, calculus, didn't they kind of broke it up into little pieces right here. And you just to find the area, you just broke this up and you turned it into a bunch of rectangles right there. And then eventually you made the width smaller and smaller right there. So, so it's kind of like, okay, so you notice if you make this width really small, then you get the nice area under the curve. But what happens if you start to make this width a little bit bigger right here? That is, if I come along here, and again, draw my curve, and you were to make them a little bit further apart, like that far apart. Well, then this goes like this. That's the area you get right there. Let's go even a little bit further. Let me make them out even a little bit further than that. Again, this thing goes up, comes back down, goes up. What if we make them like that far apart? Then you get. And what if we even make them this big right here? You'll notice if I keep making them bigger and bigger, this total area is going to get back down smaller and smaller again. So why don't what I want really small at big frequencies. So why don't we make the width of these, the delta E, why don't we make it some constant times the frequency? That way, when the frequency is really small, you're really close together and you get the nice perfect area, which is what I wanted because it fits really good over here. But then, when you get to really big frequencies, this gets much bigger, these pieces, and you can see if my pieces were, let's say, really big right here, they were like from here to there, then this would be like this, and then you get that, and so on. So you'd barely get anything. So that's what he said. This would at least solve what I want right here. If I just let my energies not be continuous, but they can only be in certain values, HF, or 2HF, or 3HF, or 4HF. So this energy, he actually said for any oscillating system, the energy can only be 0, or HF, where H is some constant, 2HF, ... NHF. So that means when I go back to this, to calculate this, I cannot use an integral. It's not continuous anymore. I have to make it a sum because it's discrete. So this now becomes the sum. So we have this average energy is now going to be the sum of, from 0 to infinity, of e to the minus e, but e we said was NHF, all over KT, times e, which is NHF, divided by the same thing, but without the e. Sum 0 to infinity of e to the minus NHF all over KT. So that's what we have to use right there. We can't use what we did before. Yeah. Okay. So how do we solve this with sums instead? Well, if you remember from algebra, 1 over 1 minus r. If I just divide that right there, 1 into 1 minus r into 1, well, 1, this is 1, you get plus, carrying this down, you get r plus r squared plus r cubed plus dot, dot, dot. So this 1 all over 1 minus r is just the sum of an infinite sum from 0 to infinity of r to the nth power. When n is 0, you get that. When n is 1, you get that. When n is 2, you get that, and so on. So it's just r to the nth power. Well, it's kind of, you noticed right here, I have something that's r to the nth power. I have a sum of, let me write it like this, e to the minus hf all over kt to the nth. This is the same as the denominator. So I'm just going to call this my r to the nth power. So this, just by using this same rule right here, is just 1 all over 1 minus my r, which is just that term. 1 minus e to the minus hf all over kt. So that tells me what the denominator is. So that's this term right here. So I'm going to take this and plug it back into here. Since this is in the denominator, this comes all the way up to the numerator. So this e average ends up being, this comes up to the numerator, 1 minus e to the minus hf over kt. And then I have that sum. The sum from 0 to infinity of, I can pull out whatever's constant. The hf I can pull out in front, so I'm going to pull that out in front. hf, we got the sum of e to the minus nhf all over kt n, right there. Okay, so how do we solve this sum right here, 0 to infinity? Well, how do we get that right? Let me let alpha for a minute just equal hf over kt. Just to simplify something for a minute. So this is just alpha. I'm just going to work with what's in the box right here. So everything in that box then is just the sum equals 0 to infinity of e to the minus n alpha, n e to the minus alpha n. Right there. That's all it is. I just turned all those constants into an alpha. Now, I'm gonna turn this also into a minus the derivative with respect to alpha of the sum of e to the minus alpha n. Now you might say, how'd you do that? Well, if I take the derivative of this with respect to alpha, it just brings down a minus n. But that minus makes it a plus n, and I got the same thing as this right here. So these two are the same thing right here. And I know what e to the minus alpha n is just right here, right? You know, where r is just my e to the minus alpha. So this just becomes minus the derivative with respect to alpha. And then this whole sum is just 1 over 1 minus r, which is e to the minus alpha. Which is, if we just take the derivative of that, we get minus, that big minus in front, and we take the derivative of this. Well, if I use the quotient rule, we got the bottom times the derivative of the top, but the derivative of the top is 0, minus the top, which is 1, times the derivative of the bottom. The derivative of the bottom is the minus, it's e minus e to the minus alpha times a minus right there. So it's just e to the minus alpha all over the bottom squared. 1 minus e to the minus alpha squared. Well, these two minuses drop out, so this is just e to the minus alpha all over 1 minus e to the alpha squared. Okay, and now I can plug back in what my alpha is right here. So this is just e to the minus hf over kt all over 1 minus e to the hf over kt squared. Okay, that's everything in the box right here. So I'm just going to put that right into here. And so we get the average energy is equal to this. But you'll notice that this term is going to cancel with one of these terms. So when I plug it in, when I plug that into here, so I'm just going to get one of these terms in the bottom. So I get a 1 minus e to the hf all over kt. There was a minus, there's a minus, there's a minus, there's a minus. Okay, because this was the minus. And then we have the hf. And then we still have this one in the numerator, e to the hf all over kt. And I think what I'll do is I'll take this e and put it in the denominator, and it becomes, that's e to the minus hf over kt. If I bring this and bring it down to the bottom, it becomes e to the plus. And I'll multiply it by each term. When I multiply it by this, it's e to the plus. And when I multiply that, it becomes 1. So this is just hf all over e to the hf over kt minus 1. So that's what the average energy is. So that's what I need to replace all of this by right here. So that means all of this right here gets replaced by what I had there. And so this becomes, plugging that all in now, J of f t df is equal to 2 pi h f cubed df. I pick up another f, and it was f squared before, all over c squared e to the hf all over kt minus 1. So there is the black body spectra. If you fit it, it follows this curve exactly right here, this curve. Now it goes back down and it fits it exactly. But we still need to figure out what that h is, that constant. Well, maybe we can get the h from right here. We said if we integrate it from 0 to infinity, that j, it should just give me this. Well, if I were to integrate this term right here, integrate this, so we're going to integrate this over all frequencies. What I think I'm going to do, I'm going to go back to my alpha. And I'm going to let alpha equal HF over KT before I do the integral. So I'm going to let alpha equal HF over KT, or F would equal alpha KT over H, or DF equals D alpha. So what I want to, actually I can just use X instead. I don't have to use alpha. X, this is X, and this is KT over H dx. So now if I put this all in terms of X right here, then this becomes, we're going to integrate this thing. So R is the integral from 0 to infinity. We can still use the same because when f goes to infinity, x goes to infinity. When f is 0, x is 0. We end up with 2. I'm going to pull out anything that's constant, so we'll pull out whatever's constant. So this is from 0 to infinity. We'll pull out the 2. We'll pull out the pi. We'll pull out the h. F cubed. F cubed is this cubed. So you got a k cubed, t cubed over h cubed that can be brought out. That's k cubed, t cubed over h cubed. Then I got a df, which is another kt over h. So that's k to the fourth, t to the fourth over h to the fourth. So I'm just going to make those to the fourth power instead. Okay, what's left inside? We still have the x cubed, which is an x cubed dx. X cubed dx. And then out here we got the c squared, can be brought out in front. We got an e to the x minus 1. Okay, so how do you integrate this thing? Well, you look it up in a table right here. You could probably use some sort of complex variables, but we just looked it up in it. I just looked it up in a table right there. And this integral is actually just pi to the fourth over 15. That's what that integral is. So this whole r is 2/15 pi to the fifth, k to the fourth, t to the fourth, all over h cubed, c squared. Now we said all of this number in front from the Stefan-Boltzmann law was our Stefan-Boltzmann's constant, which was our sigma, which we knew the value of. Since we know the value of sigma and we set it equal to all this and we know the value of everything here but h, we can get what h is. H then is equal, it's called Planck's constant. Planck's constant, and it has it's 6.6 times 10 to the minus 34 joules seconds. It's an energy times a time. If we wanted to use, remember another unit for joules was an EV, we could have used that, then it'd be 4.1 times 10 to the minus 15 EV seconds. This is a very fundamental constant. This will come up throughout the rest of the whole course right here. This is just as fundamental as big G is for gravity right here. So it's very fundamental right here. And so now we know what this thing is. And so what does this say? This says that, what did he say? He said that A, where was it? Right here. This is the big shot of the whole thing. Energy of an oscillating system can only be these values right here. So that means if you look at something like a pendulum, or let's say instead of a pendulum swing, you just have a mass on a spring. And you pull it back and it's going between here and here. And let's say it's losing energy. If it's losing energy, it's losing amplitude right here. And usually you think energy is a continuous quantity and this thing would continuously move down. But it can't. Energy can only be in discrete jumps. So it can only be in this amplitude or this one or this one or this one. So it swings and then it jumps to a smaller one and then it jumps to a smaller one and so on. The only reason why we don't notice it is because this is a very small, this h was a very small number. So if this block were swinging back and forth at 1 hertz, 1, and this h is 6.6 times 10 to the minus 34, that means it would be losing 6.6 times 10 to the minus 34 joules at a shot, and there's no way you're going to see that. It looks way too continuous for on the big scale. But when you get down to the very small scale, now it's going to become noticeable, this graininess of energy right here. Now, on one of your homework questions, I actually asked you to prove this and find that constant right there. So how do you find that constant? How do you find the peak in the wavelength? Well, what I would do here is I would convert this into wavelength instead. Instead of frequency, we know wavelength is c over the frequency, or the frequency is c over the wavelength. So every place you see a f, replace it with this, and every place you see a df, you're going to replace it with you don't need to worry about the minus, I just told you the direction of it, but the magnitude of this would just be c over lambda squared d lambda. So what would this look like if you switched all these over? That means this would look like you'd still have the 2, still have the pi, you'd still have the h. Instead of f cubed, you'd have c cubed over lambda cubed, c cubed all over lambda cubed. Then you got a df, which would be another c over another lambda squared. So you have another c over a lambda squared. That takes care of the whole numerator. Then you got a c squared. And then over here, you get an e to the h, and then f you would turn into c over lambda, so it would be hc over lambda kt. Lambda kt minus 1. Okay, so that's, and then there'd be a d lambda in there too, d lambda. Okay, so this is what it is in terms of that right there. And actually, we just want to know where this thing peaks at right there. So because that's what we want, the peak wavelength. That's going to go up and come back down. It's going to go up and we want to find it right there. So what you would do is you would take the derivative of that with respect to lambda. Take the derivative of this with respect to lambda. Set it equal to 0. What I would probably do to make it a little bit easier for you is let x equal to hc all over lambda kt, and turn all of your lambdas into x's right there. So then you would just take the derivative with respect to x and set it equal to 0. And then when you set that equal to 0, all these constants don't matter right there. And what you're going to end up with is, you're going to end up with a transcendental equation. I don't know what it is exactly, but let's just say it's e to the x equals 1 minus x. I doubt if it's that because I'm just making this up. It's going to look something like this. And now you say, well, how do you solve for x out of that? You can't say take the natural log of both sides because this would come out, but then you'd have natural log of x's. They're at different levels. You can't get them at the same level. So how do you solve something like that? Well, the one way you can do it is just graphically. If you just graphed out the left-hand side, e to the x, what does that look like? Actually, let me make it something like 3 minus x. I'm not sure what it is right here. But e to the x looks like this. 3 minus x might look like that. There would be the solution. About the only way you can, this is the way you usually solve these. You just graph the one side, graph the other, and see where they intersect and try to grab it as best you can right there. So that would be your x. And once you get x, then hopefully you're home free right there. And then you can show that lambda t is a constant and what that value is right there. So this was a long derivation just to show that E was equal to NHF. We don't know why this is true. It actually took Einstein to figure out why the energy of the oscillators in the walls of that cavity can only oscillate at those frequencies. Okay, but that's for the next time.